Hello, this is an IB explainer video on how we derive the expression for centripetal acceleration. I've recorded this because I know it's one which confuses students a lot, and it's also quite a confusing topic in general. So hopefully this is going to bring a bit of light to it. You will need a little bit of maths, and we'll be applying a few sort of bits of geometry which you may be aware of from your maths course. So let's get started. So imagine we have some centripetal motion. Okay, in other words, circular motion. Now what we can do is we can imagine the velocity vector, this red vector, at different points of the motion. And we notice that at every point, the velocity vector is a tangent to the circle. Okay, it's a tangent to the circle. I've also made sure that my velocity vectors are all the same size because they have the same magnitude. One of the features of uniform circular motion is that the value or magnitude of the velocity stays the same as we go around the circle. We can then think about the velocity at two different stages. Let's call them A and B. We have VA, so that's over on this right-hand side, and then VB, and that would be the next one here. I've deliberately exaggerated the difference, and what we'll be interested in there is reducing down this difference. If you notice here, we've got VA and VB, and again, I've drawn my, it may not appear so, I've drawn my vectors so they have the same magnitude. And that's again because the velocity is the same at all points. The magnitude is, I should say. Now, if we're going from velocity A to velocity B, i.e. from initial to final, then what we can define is a delta V. And delta V is just the vector we add to A to make B. Now you notice that I've deliberately drawn this, okay, VA is plus delta V is VB. I've drawn this so that we can relate angles. Firstly, if you notice that over, during the circular motion, we subtend an angle delta theta. The reason I'm calling this delta theta is because this theta will eventually become very, very small. It's a change in an angle. We've got a delta theta here, and just by some similar angles, you should be able to see that delta theta is also the angle between these two vectors. Okay, we can then get rid of my circular motion point, and then assume here that we've got a right-angled triangle. That's going to be important because we can then do a little bit of maths. If we've got a right-angled triangle, then, and we know that this is the angle down here, well, sine of that angle, sine of delta theta, is simply the opposite divided by the hypotenuse. Now in this case, the hypotenuse is VB, but we've said that the VB and VA are the same, and I'm just going to call them V. Okay, their magnitude is just V. We have delta V divided by V. Now, one mathematical identity we can use is an identity assuming that delta theta becomes very small. As delta theta approaches 0, the value of sine of delta theta starts to approach the value of delta theta. Sine of 0.000001 is just 0.000001. Okay, so we can replace delta theta, sine delta theta, sorry, with delta theta in the expression above. We then think, well, if we divide both sides of the equation by delta t, we've got the delta theta divided by delta t is equal to delta v over v, and then we've got an additional delta theta in the denominator there. Why do we do this? Well, if you notice here, this is delta theta divided by delta t, which is the rate of change of the angular displacement. That, in other words, is omega. Okay, we have omega. Then we take out our two deltas and multiply by this 1 over v term. We've got delta v over delta t. Well, delta v over delta t, as you should know, is also another term for the acceleration. So we're then left with an expression which says omega is equal to a, some acceleration, divided by v, the speed, or the magnitude of the velocity. And then I can just rearrange this. I can get a, the acceleration, is equal to v times omega. So this is our derivation of that formula that we use for the centripetal acceleration of a body. What we've done here is we've constructed a triangle. we've taken the limit that delta theta approaches 0, and used a mathematical identity, and then substituted in, rearranged, and then we're left with our A equal to V times omega. Now, as I say, there are multiple ways of doing this. If you look in the Oxford textbook, you will find a slightly different approach. Both are fine. In both cases, we use some mathematical tricks to get to where we want to. However, what you will find is that this equation works very, very well with the experimental practice as well. It's verified, and so therefore it's taken as a concrete piece of theory when we're studying circular motion. I hope that's of some help. Please feel free to contact me if you need any further explanation.